Good morning, everybody, and welcome to the CEIA Free Maths Tutorials. CEIA is a group of about 50 companies in the Cork region, advanced manufacturing companies. These companies provide volunteer engineers to do the tutorials. Today we've got Jerry Sweeney and Edmund Collins taking the introduction with some very essential indices and logs. So I'm going to hand you over now to Jerry Sweeney, who's going to start off with the introduction.
Good morning, everybody. My name is Jerry Sweeney, and I'm a graduate electrical engineer from UCC. And my career has spanned working in electronics and software. I started out on the electronic side, but I ended up in computers and software. And I'm now managing director of CloudKicks Limited, which is a data center here in Hollyhill in Cork. And my responsibilities extend all the way from the electrical power and cooling infrastructure to the networking, data infrastructure, cybersecurity, and software. I am passionate about technology and technology in general and mathematics in particular. Throughout my career, I have found them extremely useful. I want to talk to you this morning. So I've been given the opportunity of doing the introductory talk for this series. And I want to explain to you what my understanding of mathematics, what mathematics is, and how we use it as a tool in everyday life. Within the natural sciences, within technology and in engineering, mathematics has been described as being unreasonably effective. It is amazing how useful it is. And that is really the focus of my conversation. I worry that when people learn mathematics as a subject, if it's divorced from the application of mathematics, then they don't think in terms of its usefulness. They don't think in terms of its applicability. And I know that some people are turned off mathematics because of the fact that they see it as some kind of gymnastics, mental gymnastics without an application. I have the entirely opposite approach. I see it as a way of extending the way we think. So in order to explain this, what I've done is I have created a little map of mathematics. So so my talk is basically going to be explaining this slide in detail. So we're going to talk about concepts or models. I will use those words interchangeably. A concept is something that we think about in our head. Once we start applying properties to concepts, we tend to call them models. But if you hear me use the word concept or model, okay, think of them as being synonyms, and I will move from one to the other. So we start out with concepts, ways of thinking, ways of solving problems in our minds. And then we add numeric properties to those models. And once we have numeric properties, we have arithmetic operators on those properties. If you have 10 apples and 5 apples, you have 15 apples. So we're adding addition, subtraction, multiplication, logs, and exponents as arithmetic operators. Then we start to deal, okay, with problems where we don't know the numbers. And we have to use algebra. We have to use we have to find missing information. And then we develop techniques. Like calculus, for example, is a technique that you've probably started. So this is using arithmetic and algebra and putting them together and constructing techniques that solve problems. And typically a technique solves a family of problems, and those problems sometimes are visible, okay, across multiple applications. The same technique may be used in chemistry and in genomics and in medicine. And some of the confusion around mathematics comes from the fact that you may be taught the technique without realizing the applicability of it. So I would ask you to just a question for a second. Have you ever thought about an application for set theory, and yet you've been hearing of set theory for a long, long time? You've been learning it in school. So the first thing we want to talk about is, we want to talk about concepts. We want to talk about how the human brain thinks, how the brain works. And we are very intelligent, relatively speaking at least, and we can understand ideas. One of the most interesting explanations of this that I've seen is a 10-minute video on YouTube. It's called Why, and it was an interview by, I think, a BBC, by the BBC, of Richard Feynman. And he was asked a question by the interviewer, how do magnets work? And the conversation very quickly turned into the meaning of the word why and how people understand concepts. And Richard Feynman described it as a concept is a framework where we allow something to be true. So if somebody says, why did Aunt Minnie go to the hospital? Okay, the answer is she broke her leg. And for lots of people, that would be enough. But if you didn't know what a hospital was, your next question would be, what is a hospital? But if you have the concept of a hospital, then you have a framework where we understand something to be true and we stop asking whys. I would encourage you to spend 10 minutes and look at Richard Feynman Why on YouTube. I think it's very interesting. So we're going to start this morning thinking through a concept that does not require numbers. So I'm going to give you a puzzle, and we're going to ask to prove something. And this puzzle deliberately does not have numbers, but it has concepts and it has a proof, and I think it's very elegant. So the puzzle goes as follows. If you have a monk who wishes to go to the top of a mountain to pray, and early in the morning he strikes off for the mountain, so he leaves, we'll say, at dawn, and he walks until dusk, and he arrives at the top of the mountain at dusk, and he prays throughout the night. And in the morning, at dawn, he leaves and returns back down to the valley. So he spends one day traveling up the mountain and one day traveling down the mountain. We want to prove that there is one point and only one point on that path where the monk passes at the same time on both days. Now, if you pick any point on the path, you can obviously see that on the way up, he walked past that point, and on the way down, he walked past that point. How do we prove that there is one point and one point only, that the monk was on the path at the same time on both days? And the way to prove this to ourselves is to imagine it as two monks traveling on the same day. So one monk would climb the mountain on the first day. The second monk would descend the mountain on the first day, on the same day. It is obvious to us, it is the end of the whys, that those monks would pass each other once and only once on the mountain path. And they would say hello and wave and continue. And using that as a concept, we have proven to ourselves that we're using a number of concepts. One is that we accept, okay, that the second day is the same as the first day. We accept that a monk walking down the hill on the first day is the same as the monk walking down the hill on the second day. And we accept that if two people are going in opposite directions on a path, okay, then they will only meet at one point. So we have solved, hopefully to our satisfaction, the problem of the monk on the mountain. And we use it because we describe the problem, or we understand the solution to the problem in terms of things that we already know. So what we'll do now is we'll go and we'll start adding numeric properties to models. And if I show you this photograph of 3 coins, and were to ask you what the numeric properties of the model associated with these coins are, that question is somewhat vague, because we could describe the coins in terms of different models. So one model would be the number of coins, and there are 3 models. Sorry, there are 3 coins. Another model might be the value of the coins, and the value of the coins is €3.50. We could also divide the coins into sets, those that have 2 metals and those that have 1 metal, in which case 2 of the coins would be in a 2-metal set and 1 coin would be in another set. So depending on the model that we're using, we have different numerical properties. But we've introduced the concept of numbers to describe the properties of whichever model we're talking about. So if my question is, how many coins are in this photograph? The answer is 3. If my question is, what's the value? It's a different model, and the answer is €3.50. So we're going to solve one question on the 2019 paper 1. And as we do it, we're going to discuss the concepts that we have, the numeric properties we apply to that concept. We're going to use arithmetic, and then we're going to use algebra. And finally, we're going to use a little bit of differentiation to solve that problem. So this is a question about windows, and specifically about a window style called a Norman window, which has an arch, which is half a disc, half a circle on the top, and a rectangle on the base. I want to introduce the concept of independent variables and dependent variables here. In this question, we've been asked to accept the independent variables x and y, where x is the radius of the semicircle on top, and therefore it's half of the rectangle on the base. We have two dependent variables, and they will be given to us in the question as well. We have the perimeter and the area. And they are called dependent variables because they can be calculated in terms of x and y. If you define x and y, then you have defined the size of the Norman window. You don't need to define the area or the perimeter because they can be derived from those 2 independent variables. In terms of arithmetic, we have 6 operators that we commonly apply using arithmetic. There are many others. The modulus operator is one, for example. But the 6 most common are plus, minus, multiply, divide, indices, and logs. And Ed will be dealing with indices and logs in the second half of the talk this morning. In terms of numbers, there are many types of numbers. And it's interesting that down through culture, the number of classes of number has increased. And different societies, going from ancient times, it's interesting to see how different number types, were added, sometimes at different historical times within the history of different cultures. it's easy to understand that this would happen. So natural numbers, I think, occur in all cultures that have any ability, okay, to work with numbers. So 1 tree, 1 cow, 1 sheep, 2 apples, 4 oranges. The introduction of 0 actually caused quite some argument in some ancient cultures. Some people claim that 0 is not a number. How can you have 0 cows? But most people grew to accept that 0 was a valid number. And then the concept of negative numbers became a problem. And negative numbers make even less sense than 0 cows. How can you have -1 cow? However, there are applications that require negative numbers, and the obvious one, okay, for a negative number is debt. If you owe money, then that can be considered to be -1. You can also, if you have something like a datum, like sea level, then you can say that you're 100 meters below sea level, and that can be represented as -100. What's interesting is that the mathematical operators work perfectly on the number system as you extend the family of numbers. So then we have rational numbers. These are numbers that can be described as a ratio of one number divided by another. An equivalent definition of a rational number is a decimal number that either terminates or reoccurs. Those definitions are identical. And then there are real numbers that include the rational integer whole and natural numbers, but also include numbers that neither terminate nor repeat. And I mentioned sets earlier, and here we are using the concept of sets to describe the relationship between the different families of numbers. So the outer complex numbers contain the reals and the imaginaries, and they contain the rational integer whole and natural numbers as well. So a concept that we've learned in national school is required in order to understand this drawing. It became obvious about 400 years ago that if you took the square root of a negative number, you did not end up with a real number. And that required the creation of imaginary and complex numbers. And they were added to the family of numbers starting about 400 years ago. Italy was where they were first dealt with in some depth. But it was people like Euler that started to use them with confidence. For the last maybe 150, 180 years, they have been considered full-term members of the number system. There are applications, just like there are applications for negative numbers, there are applications for imaginary and complex numbers, especially in areas of electrical engineering, such as dealing with waveforms, repetitive waveforms. The number system is extended using the arithmetic operators. So if you if you introduce subtraction, you create the need for 0 and you create the need for negative integers. And if you have the divide by, then you create the need for rational numbers. Division creates the need for rational numbers. Irrational numbers can be generated by square roots, for example, and reals are the intersection of rational and irrational numbers. Imaginary numbers come from taking the square root of negative numbers. And since every negative number is a positive number multiplied by -1, then we can manage all imaginary numbers using the square root of -1 as a multiplicand. So imaginary numbers consist of what looks like a real number followed by the lowercase I. Complex numbers consist of a real and an imaginary part. So they are a two-part number. But I want you to be clear, it is not two numbers. So it's not like X and Y in Cartesian coordinates where they are two numbers. It is a single number. So 2 plus I is one number. It's not two numbers. So we have introduced numbers and we have discussed operations on those numbers. And we've applied numbers to models. So we're going to move on now and talk about algebra. I want to start dealing with missing data. So algebra is dealing with unknown numbers, independent and dependent variables. And it's also about dealing with relationships between those variables, equations and inequalities, and functions. And we'll give you examples of equations and inequalities and functions in a moment. I like puzzles, and this one I heard first of all when I was 14 years of age. And I found it very, very difficult to solve. It took me quite a while. But after I solved it, I looked at it again and I wondered if there was a way of solving it simply and mathematically. And I had just learned about simultaneous equations and solving simultaneous equations. And I was curious to know if I could find a way of translating this into a very simple mathematical problem. So it's a puzzle. It's intended to sound confusing. And what we're going to do is by using algebra, by using variables, we're going to try and turn it into a very, very simple problem. So Alice is twice the age that Bob was when Alice was the age that Bob is now. Alice is 36. What age is Bob? I'll read it again. Alice is twice the age that Bob was when Alice was the age that Bob is now. Alice is 36. What age is Bob? And the reason why this is confusing to me is because there's a lot of information, but there's no simple model that I can hang the problem on. So we're going to take this technique called simultaneous equations and see if we can apply it. So the first thing we have to do is we have to extract the variables. And it looks to me like there are 4 variables. Alice is, Alice was, Bob is, and Bob was. I'm going to take it that there are 4 independent variables here. Those 4 independent variables can be turned into 4 unknowns in 4 equations. And that suggests that can be solved. So Alice is twice the age that Bob was. AI is equal to 2 times BW. When Alice was the age that Bob is now. So that's telling us that Alice was and Bob is are equal. So Alice was the age that Bob is now. Alice is 36. So I suppose you could say that that's really a defined constant. It's not a variable, but we'll treat it as a variable for now. And what age is Bob? But to make it equal to Bob is, I've reversed it. So 3 of the equations are written in English in the question. Alice is twice the age that Bob was, is the first formula A. Alice was the same age as Bob is the second equation. Alice is 36 is the third. Now the fourth equation is not contained in the question, but it is in our understanding of how age works. So if you think about it, we'll have an aha moment. If you have a sibling that is younger than you, as both of you get older, the age difference stays the same. So the difference between Alice is and Alice was must be equal to the difference between Bob is and Bob was. So the fourth equation is not contained in the puzzle. The fourth equation is something that we know about the model or the concept of how age works. As an aside, I would like to tell you that if you go on and study Einstein's relativity, you will find that that fourth equation doesn't always hold if one of those parties is traveling at a velocity which is different from the one that the other is at. But I'm only bringing that up to show you that in a different model, okay, that may not be true. But for the vast majority of people, they're quite willing to accept that the delta age, the difference in age between two people remains the same regardless of the age of the two people. So we have our 4 equations, 3 from the question and 1 from our understanding of the concept or the model of time. We can now solve those equations. So if we take equation A and C and just plug Alice is into equation A, we get 36 equals 2 times Bob was. So Bob is clearly 36 divided by 2, which is 18. If we then take equation D and equation I, if we take equation D and what we worked out in equation I, so that we have Bob was is equal to 18. And we plug Bob was equals 18 into that formula. We have Alice is 36. Alice was, we don't know. Bob is equal to Alice was, so we can subtract out the Bob is, or we can replace it with Alice was. And if we bring the 18 to the left, we get 64. And if we take the minus AW to the right, we get 2 times AW. So we get 64 is equal to 2 times Alice was. Therefore, Alice was is equal to 27. We can now take the fact that Alice was 27, which we derived from 2, and plug it into Bob is, and we find the answer we were looking for. We find the answer that Bob is 27. So what we've done there is we've taken a technique in algebra, which is solving simultaneous equations, and we've applied it to solving the problem. We required to have a model or a concept in our heads as to how dates, times, and ages worked. So we're back to our question, our Norman window question. So this is taken from the 2009 paper 1. And we are given 2 variables, X and Y. Those are independent variables. You can change x regardless of what the value of y is. But we are to calculate p in terms of x and y, where p is the perimeter of the window. This isn't said in the question, but being an engineer, I like to think about it this way. If we were manufacturing a window, it's possible to consider that we might be interested in the perimeter for two reasons. One is that if the perimeter is made of a metal like aluminium, there may be a lot of heat loss through the perimeter. So we might want to minimize the perimeter for that reason. We might also want to minimize the perimeter if it was very expensive. So if the metal was expensive, we might want to manage the amount of metal that we use to construct the window. And if I could take a small aside for a moment, a number of years ago, I did a project to calculate the lengths of different extrusions that needed to be cut in order to manufacture a set of windows. So a salesperson would go on site, would visit a house that wanted replacement windows. They would take measurements of maybe 14 or 16 or 20 windows. They would be typically in terms of an X and a Y, but you might also have what are called transoms, which are horizontal bars, and you might have openings. So there were a number of window types, and there were a number of independent variables that defined each type. So that information would be collected by a salesperson, and that person then had to come back to the factory and cut the extrusions from which the aluminium window was manufactured. And there was a lot of work, and it was very error prone to calculate each extrusion length that needed to be cut. So for 20 windows, you might have 150 or 200 extrusions that needed to be cut. And what this program did was it took in the list of windows that were to be manufactured, and using arithmetic, it calculated the length of each of the pieces of metal that were required to manufacture all of the windows. It grouped them into particular types of extrusions that could be cut together. And you knew then that if you took that list of materials and produced those, you could then take those materials to the workshop, and you knew you could manufacture those exact windows. So in a former life, I spent a couple of weeks, developing that software. So I suppose I'm attracted to the idea of windows and window manufacturing as a result. So let's try and figure out what the perimeter is in terms of X and Y. So all we have to do is add up the different lengths of the outside of the window. So the base of the window is 2x because the radius of the circle on the top is x, and it is a half a circle. So we know that the base of the window is 2x. There are two sides to the window, two vertical sides to the window, each of y. So we have a term 2y, and then 2 pi r is the circumference of a circle. So the circumference of half a circle is pi r, and in this case r is x. So we can add in pi x, and we now have the perimeter of the window, P, in terms of X and Y. Highlighted in yellow there is that formula written with the 2 plus pi separated out from the X. So it's 2 times Y and 2 plus pi times X. Now it asks us to consider a particular window, which is a perimeter of 12 meters. And it's asking us to show that if the perimeter is 12 meters, then it wants us to get a formula for y in terms of x. So one of the dependent variables is now fixed at 12, and it's asking us to then find to find the function of y as for each value of x as an equation, as a function. So what we do is we take the formula that we had for the perimeter of the window, and in the first line on the right hand side there, we write 12 as the perimeter, and we write down 2x plus 2y plus pi x is equal to 12. We want to get a function in terms of y, so we're going to bring y to one side, and then we have to divide by 2 to change the 2y to a single y. So we end up with a function for y in terms of x. And a function is a particular type of equation. It's an equation where if you put in any value of x, you get one value for y. I want to draw your attention to the constraint in the question. It says, show that y equals 12 minus 2 plus pi times x over 2 for x less than, for 0 less than x, less than or equal to x, less than or equal to 12 over 2 plus pi. You're asked to show this, and it makes the question very easy because you're actually given the answer. So if you make a mistake in deriving the answer, you know you've made the mistake. But what I want to draw your attention to is I want to draw your attention to the fact that it specifies a range for x. Now, the first value of x, or the value that x must be greater than or equal to, is 0. And it's easy to understand that. It's impossible to imagine a window that has a negative width. So I think it's reasonable to assume that x is greater than 0. It's more interesting to look at why x must be less than 12 divided by 2 plus pi. And the reason for that is that if x gets bigger than that value, then the perimeter must be bigger than 12. But we've defined the perimeter as being bigger than, as being equal to 12. And therefore, there is a constraint that x cannot be above a certain value. So you can imagine that what would happen if x was to get to 12, then y would have to go to 0. Sorry, not if x was to get to 12, but if x was to go to its maximum value, so you would then end up with a Norman window which had no height. So the constraints are interesting there, and there is a minimum value that x can go to, which is 0, and there is a maximum value that it can go to, which is 12 over 2 plus pi. So we have established, okay, the function that defines it defines y, it's the function of y in terms of x. And the next part of the question is to fill in this table. And x can go from 0 to 12 over 2 plus pi. So we have to get the value for y where x is equal to 0. And that's, if you look at the formula, y is equal to 12 minus 2 plus pi times x. then the minus 2 plus pi times 0 becomes 0, and we simply get 12 over 2, which is 6. If we then take the value of 12 over 2 plus pi, we find that, and we plug that in, okay, for x, if we multiply out the 2 plus pi multiplied by the 2 plus pi, we get 2 plus pi multiplied by 12 over 2 plus pi in the minus term above the line. The 2 plus pi's cancel out, and we end up with minus 0. So, sorry, minus 12. And 12 minus 12 is 0. So 0 over 2 is 0. So for x equals 12 over 2 plus pi, the value of y is equal to 0. Now, in the exam question, you are asked to draw the graph, the linear function, and you're given 2 points. Now, in the question, it told you that this was a linear function, so you know that it's two points joined by a straight line. But if you look at the function, you will see that it is a constant times x, and that is a clue, okay, that it is a straight line. So this is how the line is drawn onto that graph. And we can see that if we assume that x must be greater than 0 and y must be greater than 0, then the only valid values for x and y are contained on that line. It's not possible for me to imagine a window where y is less than 0, and it's not possible for me to imagine a window where x is less than 0. But interestingly enough, the arithmetic will allow you to work with those values, but they have to be constrained because the model in our head doesn't allow us to extend to those values. So the third part of the question is to find the slope of the graph correct to 2 decimal places. And you will remember that the formula for the slope of a line is y2 minus y1 over x2 minus x1. And a little bit of calculation, okay, yields minus 2.57 as the slope of that line. The question also asks you for an interpretation of the slope of that line. And the interpretation taken from the solution guide is very concise and very precise. And I would urge you to spend some time thinking about it and be capable of copying that format for an interpretation for a line. So for each 1 meter rise in the radius of the semicircle, the height of the rectangle falls by approximately 2.7 meters. Actually, that's a mistake. That should be 2.57 meters. So if you have a line, okay, that is trending downwards, m is negative, then as x increases, y is decreasing. We've dealt with the perimeter of the window. What we're now going to try and do is get a function for the area in terms of x. So we're going to get a function a of x. And the question is very generous because they give us the answer. They just ask us to show that a of x is equal to, and they give us the formula. All we need to do to derive this function, we we are told, okay, that we're only interested where the perimeter is a constant 12 meters. So earlier, we derived a function for y in terms of x. So all we need to do is to find a formula for the area and substitute the formula for x instead of y. So the area of the Norman window is 2 times x multiplied by y, that being the rectangular part. And the semicircle is pi x squared divided by 2, because the area of a full circle is pi r squared, and r is x in this case. So it's pi x squared divided by 2. That is the formula for the area for the dependent variable A, area, in terms of the independent variables x and y. Given that we now have a known perimeter of 12 meters, we can substitute 12 minus 2, left bracket 2 plus y, 2 plus pi, right bracket x divided by 2. And simplification yields the function that we were required to demonstrate. A of x is equal to 24x minus pi plus 4 times x squared divided by 2. There's one more part to this question that we will come back to later. So what we're going to do now is we're going to discuss techniques. And we have, to a certain extent, okay, we have been applying some very simple techniques right now, but we're going to start talking about more complicated techniques. And a technique is a recipe that solves a particular class of problem. And the same class of problem can turn up in many disparate areas. One of the issues with teaching and learning mathematics that I have noticed is that people are taught techniques without an understanding of the application of those techniques. And the applicability or the usability of mathematics is not obvious. Some people don't have any mental issue with that. They enjoy the techniques, they love them, they see them as mental arithmetic, and they think it's great. Other people find that they're not applicable. Because I'm a more natural engineer than a mathematician, I love understanding the application of techniques. The Leaving Certificate syllabus extends what you learned for the junior certificate syllabus in a number of ways, in a number of areas. It extends the number system to include imaginary and complex numbers, and it introduces calculus. And when calculus is taught, it's taught in terms of differentiation and integration. Or I should say, those are the two parts of calculus, that integration and differentiation. And one of the issues, I think, with differentiation and integration is that they are very, very powerful techniques. But when you're learning them, it may not be obvious what those techniques are used for at all. And you may find that you're learning them from a rote perspective. You know, you're learning them as ideas and not understanding the applicability of them. And what I would like to do is I would like to talk a little bit about differentiation and integration in terms of real world applicability. Just covering imaginary and complex numbers, because these are on the syllabus for the Leaving Cert as well. When you were solving a quadratic equation for the junior certificate, you were warned, okay, that if b squared minus 4ac was a negative number, then you had made a mistake and you were to go back and redo the math. So in the Leaving Cert, it is quite acceptable for b squared minus 4ac, known as the discriminant, to be negative. But when it's negative, the result for x is a complex number. So you did come across imaginary numbers, or you may have been obliquely warned about them, okay, earlier on. And in fact, this is the application where they started to appear back in the Middle Ages in Italy. I've covered the content of this slide when we were talking about number systems earlier. The square root of -1 is I, and since all other imaginary numbers can be written as a positive number multiplied by the square root of -1, then all we need to deal with imaginary numbers is have the letter I representing the Greek alphabet letter iota written after the number 3. And I and all multiples of I are called imaginary numbers. And complex numbers have a real and imaginary part. So a complex number is a number that has both a real element and an imaginary element. And I want to repeat, okay, that a complex number is a single number, even though we write it as a double number, a plus ib. And when we work on complex numbers, especially in what's called an Argand diagram, it might look like a pair of numbers, but I don't want you to think of it as a pair of numbers. I want you to think of it as a single number that has two components. And a lot of mathematicians, including Gauss, okay, consider that the word imaginary is the wrong word that should be used. Oblique, okay, is a word that's sometimes recommended, meaning at right angles to. So it's a number at right angles to another number. And if we are to describe complex numbers on what's called an Argand diagram, then the number line becomes a number plane. So the Argand diagram is a number plane. So again, in national school, you were introduced to the number line, and rational and irrational numbers and negative numbers, they were all added, okay, to the number line. And we now have the number plane. And we need a number plane because numbers are now two-dimensional. And what's bizarre about it is that all of arithmetic works. Everything works. Addition, multiplication, subtraction, it all works. And all we have to do multiplication, for example, is to remember that I squared is equal to -1. So here we have two complex numbers being added in the first example, 5 plus 3i plus 3 plus I. You add the real parts, 5 plus 3 is 8, and you add the imaginary parts, 3 plus -1 is equal to +2. So we get 8 plus 2, I. If we want to multiply, then we use the same multiplication technique, okay, that we used earlier, or that we used with any, multiplying you would have used this when you were, if you had the roots of two variables, and you were multiplying them out, okay, to get the quadratic equation, okay, you would use this same technique. But the important thing to remember is that when you multiply plus 3i by minus I, you get minus 3i squared. And since I squared is equal to -1, minus 3i squared can be written as plus 3i. When you bring the i's together, you get minus 5i and 9i, you end up with plus 4i. When you bring the plus 3 and the 15 together, you get 18. So 5 plus 3i multiplied by 3 minus I, multiplied out comes out at 18 plus 4i. So we almost had to learn nothing else in order to get that to work, to get multiplication to work. So the amazing thing is that The arithmetic operators work for negative numbers. The arithmetic operators work for imaginary numbers. The arithmetic operators work for complex numbers. I want to talk a little bit about calculus. I want to try to give you an insight into calculus. So I have three kids, and to help them to understand calculus, I first started talking to them about calculus when we were driving. Because there is in a motor car, there is something that is a beautiful application of differentiation and integration, a beautiful example of calculus. So if you're driving in a car, you have a speedometer. And the speedometer is the speed at which you are traveling at this instant in time. So if you look at the drawing that I have there, velocity v is in the middle of the drawing, and that is the speed. So if you're doing 100 kilometers an hour, then your velocity is 100 kilometers an hour. Also on the dashboard of the car is, I think it's called an odometer, which is the number of kilometers that the car has traveled since it was manufactured. And what you're doing is you're integrating the velocity that the car is traveling at in order to get the distance that it has traveled. So if you're going very quickly, if the velocity is high, then the number of kilometers that the car has traveled since it was manufactured will increase more quickly. But if you think about it, the displacement or the odometer in the car is measuring the velocity by time of the car since it was manufactured. So integration, if you integrate velocity, you get displacement. And if you differentiate displacement, you get velocity. So for example, if your speedometer was broken, but the odometer was working, if you were traveling at 100 kilometers an hour, then the displacement, the odometer would change 100 kilometers in an hour, and you could deduce your velocity from that. So what you're doing is you're doing differentiation. Now, if you differentiate velocity, you get acceleration. So acceleration, when the car takes off, I got a spin in a Tesla Model S once, and the guy driving it put it into, well, I can't remember what it was, ludicrous mode it's called, and he put his foot to the board, and I was pushed back into the seat. I nearly got sick. The acceleration was very high. So obviously our rate of change of velocity, which is acceleration, was very high. And if you differentiate velocity, if you get the rate of change of velocity, okay, then you are looking at acceleration. There is an accelerometer in a car, and it is in the steering wheel. There's probably a couple of them in every car nowadays, and it's associated with the airbag. So if the car stops incredibly quickly, then that will be a huge reduction in velocity over a very short period of time. And that will cause the airbag to inflate. So when you're sitting holding the steering wheel of a car, you have something to think about in terms of differentiation and integration. So velocity is what you measure in the speedometer. Displacement is what you measure in the in the odometer. And acceleration is the rate of change of velocity. Velocity is the rate of change of displacement. And displacement is the amount of ground you've covered over a period of time as a result of your velocity. And velocity is the change over time, the accumulated change over time of acceleration. This is an example trip in a car where you travel at 4 meters per second for 4 seconds, and you accelerate at 4 meters per second for 4 seconds, then you hold your speed constant, and then you decelerate, and then you accelerate again, and then you cease acceleration. So the bottom graph on the bottom left is whether you have your foot on the accelerator going forward or going in reverse. So what actually happened here is the car accelerated quickly forwards. It then stopped for a couple of seconds. It then it stopped accelerating. It didn't stop, it stopped accelerating. Then it accelerated in reverse. So that might have been it running up a hill, or the person might have put it into some kind of reverse gear if it was a train. And then it accelerated again. Now, if you look at the middle graph, you get the velocity. And if you look at the top graph, it's actually a graph of distance traveled. And you can actually get a sheet of paper with some graph paper, and you can sit in a car and work this out. If you get the speed and you plot the speed every 10 seconds and draw a graph, then the area under the curve will be the distance that you have traveled. So that's just now, calculus was invented by two people more or less simultaneously. Newton and Leibniz, I think, was the name of the other guy. And they were both dealing with this, bodies in motion problem, things moving, when they invented calculus. So it's not a surprise that calculus is used in problems relating to velocity and acceleration and distance traveled. But it is applicable in lots of other cases as well. Now, what we're going to do, because the problem on the 2019 paper 1, question 9, it included a request to calculate or to find the maximum area that you could have for a window given a perimeter of 12. We're going to use that information, okay, to find out what the biggest window that we can produce for a given perimeter is. And what I want you to notice here is that the curve f of x here is a parabola, and if you differentiate a parabola, you get a straight line, and at the maximum of the parabola, you have zero rate, you have a zero slope, and therefore the f dash x, or the dy dx value at that point is equal to 0. So if you want to find the maximum of a function, if you differentiate it and find where the value where the function that you differentiated goes through 0, then you will have found the maximum. So the maximum of a function matches where the differentiated value goes to 0. And we're going to use that in order to find the maximum. And in the Leaving Cert most years, there is a question that requires you to find a maximum. So it's worked out here. I hope you can see my mouse as it moves. So earlier on, we found the formula for a of x. This was an earlier question. Now we have to differentiate it. Some of you will have done differentiation. I think most of you. If anybody hasn't done differentiation yet, don't worry about it. But what you do when you differentiate, don't worry about not understanding it, it will come. When you differentiate x squared, you get 2x. When you differentiate x, you get 1. So the a dash, if you differentiate the function a of x, you get a dash x. And this function then determines, so we simplify it and we get 12 minus pi plus 4 over x. We are looking for where a dash x is equal to 0, because a dash x equals 0 is where, so the brown line there is a dash of x, or f dash of x, and the red line is f of x. So if we find where a dash of x is equal to 0, then, so we'll move from the red box now to the green box. We defined a dash of x equals 0. Therefore, 12 minus pi plus 4x is equal to 0. Therefore, x is equal to 12 over pi plus 4. If you get a calculator, you can work out that x is equal to 1.68, but it's more important right now to remember that it's exactly 12 over pi plus 4. We also got a function for, if the perimeter was a constant 12, we got a function for y in terms of x. So what we can now do is take that formula and plug in 1.68, and we simplify it down. This is pure arithmetic. Pi is not a variable, this is pure arithmetic. And if we do the formula up here, we get roughly 1.68, but it's more intuitive. It's better if we actually do it without taking a simplification for pi. And we find out, okay, that y is equal to 12 over pi plus 4. So what that means is that if y is equal to 12 over pi plus 4, which happens to be equal to x, then we have maximized the size of our window for a given, for a particular perimeter. So, so that means that if we want to make windows that are the maximum area for the perimeter, then all we need to do is make x equals y. So we can have a window as big or as small as we like. And yet the simplification is that x is equal to y. So you can imagine, so this is part of the unreasonable effectiveness of mathematics. Okay, we have now found a very simple rule to manufacture windows that are optimized in terms of the amount of glass versus the perimeter. And in the case of a Norman window, it's x equals y, which can be remembered easily for somebody who's making Norman windows. So this is terribly elegant and terribly cool. All right, I think I'm coming to an end. So just to say that those applications are the techniques that you learn. Okay, we've just done calculus as a technique there, are applied in chemistry, economics, engineering, almost any technology you get into, software development, whatever, all of these techniques will be used. So I'm going to say thank you, and I'm going to hand back to Eamon. Thanks very much, Eamon.
Thank you, Jerry, for a very interesting presentation. For now, we're going to have a short break. Welcome back, everybody. And to take the second part of the this tutorial, I'm going to bring on now Edmund Collins, who is a very experienced mechanical engineer, and he'll take the second part of this tutorial.
Thank you, Eamon, and good morning, everybody. My name's Edmund Collins. I'm a chartered mechanical engineer. I've worked a lot in maintenance management and energy and utilities management as well. So I'm very pleased this morning to be giving you this tutorial on indices and logarithms, or logs as they're commonly called. As Jerry mentioned, he's very interested in applying the theory to the practical applications, and likewise am I. I try and use, where possible, good theory in helping solving engineering problems, because we spent a lot of time studying maths, sciences, technology, and so on. And it's good then to be able to apply that theory to everyday problems. And it's interesting this morning that we'll be looking at indices and logs. Particularly indices are used extensively within engineering and science. When any time you're dealing with different dimensions, for example, if you're changing from milliliters to liters. If you're dealing with pressures and so on, the indices come in there quite a bit. So it's important to be very comfortable with using indices, and logs are the second part of the one coin. On one side you've indices, and the other side you've logs. So really, before working on logs, it's important that you're quite happy with indices. And certainly indices will come up indirectly in a lot of the questions in the Leaving Cert, and logs directly. Later on in the tutorial, I'll go through some questions from past Leaving Certificate papers, which are directly related to logs. I picked out a number, but if you go through those papers, you will see that there certainly will be parts of questions that would require extensive knowledge of how to use logs. So in order to not to lose time during the exam, it is important that you're comfortable working with these tools. And we often talk about the techniques, and Jerry talked about this, the different techniques we use. We can think of them as tools in a toolbox. So when we go to solve a problem, it's like trying to fix a washing machine. So we take out a screwdriver, we take out a pliers or whatever. And likewise, when we're dealing with a problem on a Leaving Cert paper, we have to be familiar with the tools that we need to use to solve the problem and how to use them. So I hope you're going to get some benefit from this tutorial, and we'll start away. So indices. So this equation here, where we see 2 to the power, what we call the power of 3, equals 8. That equation, that's a form of indices. So in this case, it's important to be familiar with the terminology. So 2 in this case is the base, and 3 is the index or the power, and 8 is the value of the power. So we'll also be talking a lot about bases when we move on to logs. So bases are very important. And when we're applying some of the laws of indices, it's important that we work in the same base. So the first law. So if we have a situation here where we've 2 to the power of 3 multiplied by 2 to the power of 2, so we've a product of 2 indices here. We can write that out simply as 2 by 2 by 2 by 2 by 2. And that in turn then can be written as 2 to the power of 5. So in summary, this first law, the law of product would say that 2 to the power of A multiplied by 2 to the power of B equals 2 to the power of A plus B. Now it's important to remember it's not A multiplied by B, it's A plus B. So that's our first law of indices. The second law, so if we're dividing two powers here, so again you notice that they're both in the same base here, in base of 2. It doesn't matter what bases they're in, but they need to be both in the same base. So again, we have 2 to the power of 3 divided by 2 to the power of 2. So if we write this out simply, 2 by 2 by 2 divided by 2 multiplied by 2, that equals 2. Now put in here to the power of 1. When we're writing numbers, we don't include the power of 1 if we're talking about a single number, but it's implied, and therefore in this case I've shown a 2 to the power of 1 there. So the second law states that if we're dividing 2 to the power of a by 2 to the power of b, then the result will be 2 to the power of a minus b. So that's the second law there. The third law, so this is where we're raising an index to another power, and it's important to differentiate that from the first law, the product here. Again, it helps to understand how the law works by writing it out in longhand. So 2 to the power of 3 squared is 2 by 2 by 2 multiplied by 2 by 2 by 2. And again, that can be written as 2 to the power of 6. So from that, we can derive that the law states that 2 to the power of a raised to the power of b equals 2 to the power of a multiplied by b. So different from the first law there. Now, the fourth law is an interesting law here. Jerry mentioned 0 and how some people back in the day might have considered that it wasn't even a number, but it certainly is here. So what's interesting here is that any number to the power of 0 is equal to 1. And some years back when I was preparing tutorials, I was trying to work out for myself, you know, how could you prove that 2 to the power of 0 equals 1, or any number to the power of 0 equals 1. So I thought of it this way: 2 to the power of 0 is equivalent to 2 to the power of a minus a, because a minus a is 0. But we know from our law of division there that 2 to the power of a minus a is 2 to the power of a divided by 2 to the power of a, which in turn is equal to 1. So you don't need to be thinking about this, obviously, when you're doing questions, but I think it helps with the understanding if you can see where this comes from. A bit like Jerry's example of the ant going into the hospital and somebody saying, well, what's a hospital, and so on. In this case, it's just good to know, well, that any number to raise power of 0 equals 1. You understand where that comes from, and then you're happy when you're working away with a problem with indices, and you have a number raised to the power of 0, you know straight away that that's going to be 1. The fifth law. So again, this could come up in dimensions if you're dealing with a physics or chemistry problem here, where you have a dimension under the line and you want to bring it up above the line to have all your dimensions on the one line, so to speak. So in this case, if you have 1 over 2 to the power of a, well, that can be written from the previous law. 1 can be written as 2 to the power of 0 over 2 to the power of a, and then again from the division law, that equals 2 to the power of 0 minus a, which is equal to 2 to the power of minus a. So that's just again another way of being happy that if you see 1 over a number to a power, you can bring it up as 2 to the minus power. And again, if it's 1 over 2 to the minus a, well, that in turn, then you can see the derivation there, that in turn equals 2 to the power of a. Now, the last example there, 1 to the power of x minus 2. And again, working it out, we see that it equals x squared. So far, this is the first time we've introduced a variable rather than a number into indices, but it works equally well. The law of indices apply to variables, x, y, p, q, whatever variable's been used, as it does to numbers. So that's why I've introduced it there. The sixth law, so it's often important that if we have an equation or a formula that we want to convert some of the variables or the numbers, whatever, into the same format. This is quite an important problem-solving approach, as you'll see later on when we're dealing with logs. So in this case, if we have the square root of x, we can write that it's equivalent to x to some power a. Now, we know from our previous law that the square root of x multiplied by the square root of x equals x to the power of 1. So x to the power of a multiplied by x to the power of a will be x to the power of 2a. 2a equals 1, so therefore in this case a equals a half. So therefore we can write the square root of x has x to the power of a half. And you've probably noticed in one of Jerry's slides that he had the square root of 2 written as 2 to the power of 0.5. So 2 to the power of a half, the same thing. So this will apply as well in the case of cube roots as well. So if we had x to the power of a third, then that's the cube root of x. Just looking at this little example here at the bottom of the slide, if we want to simplify an equation here where we have, or a statement where we have 4 to the power of 3 over 2, that can be written using previous laws. It can be written as 4 to the power of a half to the power of 3. Then we can simplify that into the square root of 4 is obviously 2, and 2 to the power of 3 is 8. So what might look like something a bit strange, how would you, without resorting to a calculator, how would you calculate the power of 4 to the 1.5? Well, this is a way to do it, just to simplify things and come out with the correct answer being 8. The 7th law, important there. So if you had 2 variables inside the brackets raised to the power of n, x multiplied by y to the power of n, well, then that can be written as x to the power of n multiplied by y to the power of n. Again, important in simplifying equations and so on during problem solving. And then finally, similar law, the 8th law, where we have x over y to the power of n, that can be written as x to the power of n divided by y to the power of n. So they're the 8 laws that are used in the indices. Again, it's important to be quite familiar with them, practice their use, and they should become second nature then when you are problem solving. So where can they be used and how can they be used? So here's an example in this equation here. We want to solve for x. So we've 3 to the power of 5 minus 3 to the power of 3 equal to x. So how would we solve that? So, well, we can simplify 3 to the power of 5 or convert it to a format similar to 3 to the power of 3 by using one of our laws, a product law there. 3 to the power of 5 is 3 to the power of 2 multiplied by 3 to the power of 3. So we put that into the equation here instead of 3 to the power of 5. And then we can take 3 to the power of 3 outside the brackets, leaving 3 to the power of 2 minus 1 inside the brackets. So then we end up with x equals 3 to the power of 3 multiplied by 8. So that's just a simple example of how indices, the laws of indices, can be used. So here's another example. Well, it's a question here really for you. So based on what we did in the previous question, I'll give you just a minute to try that question yourself. So hopefully you have some pen and paper, or you could work it out in your head. But here is this question. So again, we want to solve for x. 2 to the power of 7 minus 2 to the power of 6. So we take a similar approach to what we would have taken in the previous example. I'll just give you a minute. So again, 2 to the power of 7 is 2 to the power of 1. I haven't written in the 1 there, but we know that's implied. Multiplied by 2 to the power of 6. So there we are there. That's minus 2 to the power of 6 equals x. So again, taking 2 to the power of 6 outside the brackets, we're left with 2 minus 1 multiplied by 2 to the power of 6 equals x. X equals 2 to the power of 6. So hopefully you were able to solve that. It's fairly straightforward, but again, builds your confidence in using the different laws. Now here's a trickier example here. So here we have 3 to the power of 2x minus 1. Getting a bit more complicated now. So this equation says 3 to the power of 2x minus 1 equals 81. So we want to solve for x. Well, the first thing we notice here is that on the 81 is in a different format on the right-hand side to the left-hand side. So what we're always trying to do again in problem solving is have both sides of the equation in the same format. So 81 is 3 to the power of 4, and 99's been 81. So once we have it in that same format, then we can actually take this part here equal to this part here. So the power, if you like, of both sides will be equal. So it's a logic there. You need to trust the logic in this. So we can write then 2x minus 1 equals 4, and then x equals 5 over 2. Bit more complicated, but it just shows you, if you excuse the pun, the power of indices and how they can be used to solve relatively tricky questions. So here's another question for you to try. A little simpler than the previous one, but in this case, both sides, they are in the same format. We've the base of 2 there, but I'll give you a minute there to see how you would solve that, again using the same technique that we used in the previous example. So again, from one of our laws, we know that 2 to the power of 3 to the power of x is 2 to the power of 3x. Again, we can see now that both sides of the equation are in the same format, both to the base 2 there, so the powers are equal. So 3x equals 4, x equals 4 over 3. So that's a summary, quick summary of the laws of indices, but really they are the gateway into logs. So if you are having trouble with understanding logs, then I would suggest that you go back, just revise indices, and then move on to logs. So we started off, the first slide is a tutorial where we had 2 to the power of 3 equals 8. Well, that's equivalent to saying that the log of 8 to the base 2 equals 3. So you can see straight away here, we're using the same terminology in terms of bases and so on. But in this case, it's the power 3 that is the log. So sometimes it's good to write logs, and when I'm working on logs, you know, if you want the log of 1,000,000 or whatever to the base 10, then I convert it back to the index form, back the number of the million, 10 to the power of 6, convert it back to index form. And I've done that here. So 8 is 2 to the power of 3, but obviously it has to be in the same base, in the base 2 here we're working with. And therefore it's quite easy to see then that the log is 3. So the base is 2, the value is 8, and the log, in brackets, the index is 3. So a technique for evaluating a log, which I've taken from one of Aidan Rountree's books, Effective Maths, very good reference books. So this is his method for evaluating a log. So just want to give him credit there for that. So the first thing is to let the log be equal to x, write the log statement in the index form, and solve the equation for x. So that's what we've done here. So there are different ways of evaluating logs, but certainly this is one good way to think in terms of converting it to index form. And certainly when you're starting off using logs, as you become more familiar with them, then you can bypass some of this. So just a little background to logs. Common logs, they're logs to the base 10. When I started using logs, it was all to the base 10. Natural logs, they're to the base e, where e is approximately equal to 2.718. And Jerry mentioned the exponential growth, very important. He's used a lot in maths, science, statistics, and so on, probability. So very important. So any log to the base, a log to base e is called a natural log. So logarithmic scales are used in chemistry for measuring pH. So any of you doing chemistry will be very familiar with the pH scale. And I think most of us would have heard, unfortunately for some people, the earthquake strength, which is on the Richter scale. And they're also used, logs are also used in the calculation of decibels, which are used in acoustic and electronic engineering. So Jerry, when he would have been studying as electronic engineering, would have come across decibels. So they're quite widely used out in the industry from that point of view. And that's where I would have come across the use of logs in my career. They can be also used for plotting data. You can use log graphs, and you do find that in technical literature and so on, data being presented on a logarithmic scale. So quite widely used. They would have, I think, they would have originated before the era of calculators and so on, and they were used particularly in navigation, I'm sure. So there were tables back in the day. They would have had tables of logs, and then they were used. The concept of logs was used with slide rules. You may have heard of those ancient things, but they did use those laws of logs that we'll be looking at now in slide rule operation. So here's an example of a log, and using the technique that Aidan Rowntree mentioned there. So so the log of 1,000 to the base 10 equals x. So we can write 1,000 as 10 to the power of 3. So therefore, the log of 1,000 to the base 10 equals 3. Now, unfortunately, it's not only the common logs and the natural logs that you're going to have to deal with when doing questions. You find logs examples in all sorts of bases. But if you're familiar with logs, it shouldn't really matter when you'll be able to work in different bases outside of base 10 and the natural logs. So here's an example where we're asked to evaluate the log of 32 to the base 8. So again, we write log of 32 base 8 equals x. 8 to the power of x equals 32. Now it's a little tricky here because as we can see, we have 8 to the power of x. We've a power here, an index. We haven't got one here. We've 8 here, with 32 there. So what can we do to simplify things? Well, we know that 8 is 2 to the power of 3. So we can write that in that way. And we also know the 32 from our work with indices will be 2 to the power of 5. We know from one of our laws of index, 2 to the power of 3 raised to the power of x equals 2 to the power of 3x. And that equals 2 to the power of 5. So again, we're on familiar territory now. We have the base is the same either side here. So the powers then will be equal. So we're back to this technique again. So you find that coming up time and time again, this approach. So 3x equals 5, x equals 5 over 3. So what looked like quite a challenging question, once you got it into this format, the rest rolls out quite easily enough. So here's something for you to try. It's simpler than the previous example, but what is the log of 9 to the base 3? Remember, we want to get things into the same format, into the same base. That's a clue to that one there. So I'll just give you a minute to think about that one and see, can you do that? Can you work out what's the log of 9 to the base 3? Okay, so again, we can write the 9 in the format 3 to the power of x. 3 to the power of x equals 3 squared, so x equals 2. So therefore, the log of 9 to the base 3 equals 2. So now we're going to go through the laws that apply to logs, and actually some of these are quite similar to the laws of indices. So you'll see this is where you see the similarity between the laws of logs and the laws of indices. So if we have two variables x and y, we're dealing in the base a here. So what's the log of x multiplied by y in the base a? Well, the first law says that equals the log of x to the base a plus the log of y to the base a. So how can we prove that? Well, we can take an example. If we take a base of 2 and put in 4 for x and 8 for y, well then we can write the log of 2 of 4 multiplied by 8 equals the log of 2, the log of 4 to the base 2 plus the log of 8 to the base 2. And when you work it through there, you see that either side of the equation are the same, so that proves the law. So the log of 32 to the base 2 is 5. The log of 4 to the base 2 is 2, and the log of 8 to the base 2 is 3. So 5 equals 2 plus 3. Very important that you're familiar with these laws again, because they do come up in questions, as you will see later on. That's the first law. The second law, so if we have the log to the base A of x divided by y, well, the second law says that that's equivalent to the log of x to the base A minus the log of y to the base A. So again, how can we prove that? Well, we can plug in our base 2 here, x over y. So let's say x is 8, y is 4. And therefore, we can see there that the left-hand side of the equation equals the right-hand side. So 1 equals 3 minus 2. And you'll notice here that something we've jumped a bit ahead in terms of one of the laws there, but the log of 2 to the base 2 is 1. So the log of any number which is equal to the base is always 1. Let's see that now in a little while. Third law, used again extensively in problem solving. So if we have the log, we're looking for the log of x to the power n to the base a. No, there's a bit in that, but that equals n multiplied by the log of x to the base a. So again, I've worked it out for you there just to show you how that applies. So if we plug 2 in for the base a, x let x equals 4 and n equals 2, we can work our way through it there and see that on the left-hand side, we end up with the log of 2 to the power of 4, which is 4, and that equals 2 multiplied by log of 2, 2 to the power of 2 to the base 2, which is also equal to 4. I've just shown those worked examples to help with the understanding of the law, but again, once you know the law, you'll be just using it away, and this is an important one. So certainly those first 3 laws are used extensively in problem solving. The fourth law, the log, an important one here, but the log of 1 to any base will be 0. And this comes back to one of our laws of indices, where we said that any number raised to the power of 0 would be equal to 1. So that's basically what it's saying there, that we can write 1 in the format of the base raised to the power of 0, any base, as long as obviously they're the same base here, but the log of 1 to any base will always equal to 0. So important to remember that. And the fifth law, which we looked at in the previous example, is that the log, if we're trying to find a number which is the log of a number which is equal to the base. So in this case, and again, I've just written in the one that has the power, but the log of 2 to the base 2 equals 1. The log of 10 to the base 10 equals 1. The log of e to the base e, natural logs, equals 1. So if you see a number in here, find the log, and it's equal to the base, the log of 6 to the base 6 will equal 1. So that's important, and that again comes up in problem solving. Sixth law here, a bit more complicated, but is used in problems. So if you have a to the power of the log of x to the base a, that equals x. Again, it might be no harm to help with the understanding is to work that out using the other laws. So this, you could have this situation where you have e to the power of ln2. So ln obviously is to the base e, natural logs. So e to the power of ln2 equals 2. So an interesting law there. And then the seventh law is a change of base law. I have seen it used in problem solving, one of the Leaving Cert questions. It can help. It's a little complicated, but it is a useful tool to use. So you may be in one base and you want to switch in order to standardize. We saw in problem solving, it's important to have standard across the equation. So this would be a useful tool technique to use to change base. So basically what we're saying here is the log of x to the base a equals the log of x to the base b, which is the new base or the base you want to compare to, divided by the log of a, which was the original base, to the base b, which is the new base. And one way to think of this is ABBA's in the news now. They're coming back as avatars. So the ABBA here, if you just think here in terms of the A, B, B, A, ABBA. So that could help if you're writing it out, just to remember the first three of the base, and then this is the base. This is the original base as well. So that's one way of remembering how to write it out. And again, if this is quite useful, if x equals b, then it can be simplified here because we know that the log of b to the base b equals 1. So if you have the log of b to the base a here, so that equals 1 over the log of a to the base b. So that's interesting in that it's switching the number and the base using that technique there. So I'd advise you being familiar with it, and you never know, it could just help you solve a problem quickly when you're doing the Leaving Cert exam. So there are all the laws of logs. So just to help put it into practice, so to speak, here's an example for you to try to evaluate a log here. And again, we're going to use indices here as well as logs and the laws of logs. There's actually a few ways of there's 2 ways of doing this question. So think of what could be done here to solve this. Remember, we want to get to we want the number 8 reading the base 2. That's the starting point there to help us solve the problem. So I'll just give you a minute there to think about that. So we know from one of our previous laws here, so we can write the log of 8 to the base 2 the power 6 has 6 multiplied by the log of 2 to the base, or sorry, the log of 8 to the base 2. Then we can simplify 8. That can be written as 2 to the power of 3. And once we're in this territory here where we have a number power here, an index, sorry, which is same base, here is the log, then we know that the log of this number here will be 3. So 6 multiplied by 3 equals 18. One other way to do this would have been to actually put in 2 to the power of 3 in here, and then a power to a power to the power of 3 to the power of 6 is 2 to the power of 18. So straight away, then that would give us the same answer there, 18. So that's just a simple question on applying using one of the laws of logs. So we're going to do something on the whiteboard here, an example, which is an interesting one because it uses the law of logs in reverse, if you like. So I'm just going to switch over to the whiteboard. So we have, can you see that all right, Eamon?
Yep, you can see that fine, Ed. Thanks.
Thank you. So situation here where we're asked to solve for x, where we have the log of x minus 3 to the base 6 plus the log of x plus 2 to the base 6 equals 1. Now, Jerry, in his presentation, was talking about real numbers, natural numbers, and so on. And one of the examples he went through, questions, talked about constraints in terms of the solution. So you need to be familiar with the terminology and the notation, I should say, that's used in exam questions. You should be by now. So we're here, what we're saying is x must be a real number. So no imaginary numbers that Jerry was talking about. And also x must be greater than 3. So what's interesting about this is that we know from the work we've done on the law of logs that the log of x multiplied by y equals the log of x plus the log of y once they're on the same basis. So we actually we're going to use that law in reverse, as if you like. So we're going to actually bring x and y back together again. So I'm using A and B here. So the log of A multiplied by B to the base 6 equals the log of A to the base 6 plus the log of B to the base 6. So therefore, we can take the log of x minus 3 to the base 6 and multiply by the log of x plus 2 to the base 6. So that will simplify one part of the equation for us. Equals 1. Now, again, it's important here to see that we have two different formats on either side of the equation. So remember from our law of logs that we can write one as the log of 6 to the base 6. So any number, the log of any number that's equal to the base will be 1. So now we're a good bit through the problem, because we can actually dispense of the logs, if you like, here, and we can write this. So again, a good problem solving technique there. And we can just work out the algebra. So x squared minus x minus 12 equals 0. So we're in familiar quadratic equation territory now. Now, Jerry mentioned this equation that's used for solving quadratic equations, where b is the coefficient of x, a is the coefficient of x squared, and then c is the constant. If you're familiar enough with factorizing, this is a relatively simple quadratic equation. You don't need to go and do this. If it's more complicated, if you had 3x squared minus 7x or something, you know, this is a good tool, but it takes a little bit of time to work out the solutions. But in this case, we can write it as so x minus 4 multiplied by x plus 3 equals 0. That's equivalent to x squared minus x minus 12. So that's simpler, saves a bit of time. And then the solutions are x equals 4 or x equals minus 3. So there's our solution. So, but remember here at the start of the question, we were required to find a solution where x is greater than 3. So obviously -3 is not fitting that bill. So x equals 4 is the solution. It's greater than -3. So hopefully that's given you some idea of how the laws of logs could be used, albeit in reverse. But the important thing here really in this problem solving, well, there were 2 steps here. One was using the law of the product of 2 numbers, and also using this law here, which says that the log of 6 to the base 6 equals 1. Once you have both sides in the same format, then you can work away, and the rest was just pure algebra, so fairly easy to work through. I'm just going back to the slides there. Can you see my screen there, Eamon?
Yes, I can. No problem.
I just to get down to the correct slide. Okay, so logs can be also used in this type of problem solving, where we have x to the power of y situation. So we see here where we have 10 equals 100 to the power of 1.2x. So again, you take logs either side of the equation. In this case, log of 10 to the base 10 equals the log of 100 to the 1.2x to the base 10. And that could be written from our previous law of logs, 1.2x multiplied by the log of 10, at the log of 100, sorry, to the base 10. And that works out as x equals 1 over 2.4. Again, situation here where you might want to solve for t. In this case, we will use natural logs. So 1 equals e to the power of 2t, solve for t. So we would take natural logs. Now, when I started using natural logs, we used to write them as ln, but I have seen them now being written as log and then e to the base e. So the notation could be one or the other. The shorthand there, ln, is just helps writing it out that bit quicker. So again, we're taking natural logs in this case because the base is e, so we're opting for natural logs here, base e. So ln1 equals 2t ln e, and t equals ln1 over 2. So that's a good. There's some good examples of how logs would be used. One thing though is very important, that if you have a situation where you might have had e to the power of 2t plus t here. What you need to do is put the brackets all around the right-hand side and take the log of that. You can't take the log of, can't write it as ln1 equals ln e to the power of 2t plus lnt. Just watch out for that, because that could catch you in some problem solving situation. Now, as I mentioned earlier, logs, indices come up definitely indirectly, but logs come up directly in exam papers. As you can see from the list there, they tend to be the questions on paper 1. I've picked out from some of the fairly recent papers, some examples there. Paper in 2016, 18, and 2020. But there are others, and I would certainly recommend you practicing the use of logs by doing questions. The more questions you do, the more familiar you will be with the laws and where to use them, how to use them. So nothing beats actually doing the questions. And there is a good resource on the Department of Education's website, which has all the exam papers going back quite a number of years. Plus, it has all the model solutions as well. But please try the question first. If you're really stuck, then go on to the solution, and it'll help you build your understanding of how the problem is solved. But it's good to attempt as many questions as possible. So we'll have time certainly for one. I'm going to start with the question from 2016, and we'll see, we might have time to do part of the question of from 2020. So I have these questions already in my report. Can you see that screen, Eamon, please?
Yeah, all good, Ed.
Thank you. Now, this was question 4, 2016, paper 1, part B. So there was 1 and 2. If I remember rightly, total number of marks was 5 for each, so 10 marks. So we'll have a go at it, but it's a good example of the use of logs here. So given that the log of 2 to the base a equals p, and the log of 3 to the base e equals q, where a is greater than 0, write each of the following in terms of p and q. So this is where our law of logs come in here. So we know from a law of division so that was one of our laws we looked at earlier. The log of 8/3 to the base a equals the log of 8 to the base a minus the log of 3 to the base a. But the question asks us, we have one of the parts of the equation in the correct format, because we can see here the log of 3 to the base a equals q, but we haven't got the other needs to be in the format of of 2 here. So straight away we can write it again. This format here. So we know that h is 2 to the power of 3, and we know from our previous laws as well that we can write the log of 2 to the power of 3 to the base a has been equal to 3 by 3 multiplied by the log of 2 to the base a. Write this in again. So we're done now, really, because we have this here in terms of log of 2 to the base a. So log of 2 to the base a we know is p. So that's 3p, and the log of 3 to the base a is q. So the correct answer to that is 3p minus q. You can see straight away there, laws, indices, laws of logs, indices. You'd really need to be very familiar with those and to get through that question quickly. So straightforward enough, that one. So the next one is somewhat similar. It's more complicated. So we're going to use our division law again. Log 980 squared to the base a minus the log of 16 to the base a. But we can further simplify the log of 9 to the log of 9a squared to the base a. That's using the law dealing with products. So that can be written as and we're going to actually simplify this because 16 is 2 to the power of 4. Now, again, another law will come in here. So the log of a to the base a, that's going to be equivalent to 1. So we can write this as 2 by the log of 3 to the base a plus 2 by 1. I'll just put in the 1 there, minus 4 times the log of 2 to the base a. And again, when we look at what we were given in terms of p's and q's, we can see that we can write the equation as this: 2p plus 2 minus, or sorry, that was 2q plus 2 minus 4p. So it's a bit trickier, but if you weren't familiar with the law of logs, then you wouldn't have been able to tackle that question. They are good examples of the application of the logs and indices coming in there. So that's why I think it's a good question to try. Unfortunately, I think we're just running out of time, so I won't have time to go through another question, but I would recommend that you try this as soon as you can, while the material we covered in this tutorial is fresh. So this question 3 from very recent paper 2020. So it's a good example of applying logs. Now, really, lots of the logs come into this part B, section 1. So that's where the logs come in. They come in a little here, but this is the part. But you could actually do the whole question. It wasn't too bad a question, actually, the whole question. But there's another example for you to try. So I hope that's been of some use, and you're a bit happier with indices and logs after going through the tutorial this morning. And thank you again for your attention, and I wish you the best of luck with your studies, and hopefully I'll see you again on future tutorials on trigonometry and probability. Thank you again.
Thank you, Ed, for a very nice presentation. Remember that you can use the log tables. You don't need to go around memorizing the formulas or the rules of logs and indices. They're there in the log tables for you. And also, I'd like to point out there's a lot of very useful resources available free on the internet. One really good one is the Khan Academy. Should be on your screens there now. And again, also the log tables. This is something that you need to be very familiar with. On page 21 of the log tables are all the rules of indices and logs, and there's an awful lot of information in the log tables. So saying that, that's all for this week, and hopefully we'll see you next week for the Algebra 1 tutorial with Paul Sheehan.